Okay, I guess we're pretty much ready to begin. First of all, any questions about anything from last class, about counting, about anything we need to talk about? Anyone wants to count? Okay, let's go through the counting problems and see how many people have done. Let's count how many people got. How many people got all 4 of the counting problems done? Okay, no one will admit to getting all 4 done. How many people have got 3 done? Raise your hand if you got 3 done. We got 2 3s over there. How many people got 2 done? Okay. How many people have 1 done? And how many people have none done? Okay. How many did you have done? 4. Okay, so you did do 4 of them. Okay, good. Let's go through the problems. So my vision is for today, I want to do 2 things. I want us to go through the problems, and at the end, I want to pass out the thing about the, let's say, the 100 problem read. So I have that assignment here. I want to remember to talk about that, but I want to make sure we go through the problems more carefully first of all. So let's look at the first problem. The first problem was counting, if I remember correct. Okay? And who's done this problem and wants to talk about it? Someone from this side of the room. They don't talk as much. Okay? Who's tried this side of the room? Problem. Has somebody done this on that side of the room? They want to tell me about the problem? Okay. Anybody? Yes, what's this problem?
People don't know how to count because when there is 4, he's a special program to count something. He count the numbers in, for example, 1, 3, 2. He add 1, 3, and 2 equal to 6 if he want to count this number. But when he read the number 4, he assume it is 1.
Right.
So we need to find the permutation. If how many permutation if we want to calculate the one answer.
You want to find out, you said, how many permutations there are that add up to a particular target integer.
Yeah.
It's really not permutations, it's really strings, I guess. Would that be the right way to think of it? So it's really strings, okay, because the digits are not unique, okay? And there's this complication that the characters are the same. Actually, I guess I have some sympathy here. I don't know my Chinese very well, okay? How do you write a 3 in Chinese? Is it this?
Yeah.
Okay. And how would be the right way to write a 2? Is it like this? Okay. But how do you write a 4? How do you write a 1? Is it like this? Okay. Like Gustavo. I don't know if it's, well, both of these I think of as 1. Okay. Any questions? Okay. So these are basically both the symbols for 1 as far as we're concerned. This is in Chinese and Skiena Chinese. This is the symbol for 2 and 3 are well defined. Any questions? Hey, how far does it go that you count like this? The only reason I knew this, by the way, is my daughter, who was taking a very tiny bit of Mandarin, pointed out that a symbol and it looked like that for 3. So I kind of generalized. How far does that go?
Only up to 3.
Only up to 3. Okay. So as you can see, I now know 3 symbols of Chinese. Okay. Any questions? Okay. So how do we solve this problem? Okay. How do we come up? We need to find a way to count how many strings there are that add up to a target. Okay? Any ideas how you go about it?
Recursion.
Say recursion. What does recursion mean? How do you propose to do this recursion?
A recursive formula.
Recursive formula, so recurrence relation. That's the magic word that I would like to think about. What is the recurrence relation that we would want to give for this?
I already know the total permutation I can have for 1, 2, and 3, and 4. I can do for myself. So then I have the first, and then I assume the first digit to be 1, 2, or 3, or 4, and I can write it.
Okay, actually, before you write it, I'll tell you how I like to write recurrence relations. Okay, just because it's easiest for me. I'd like to start out by defining what it actually is counting in English. Okay, so we're defining something like f sub n is going to be equal to the number of strings adding to n. Is that right? Okay. And now what you're proposing is you're saying that there is some initialization, or are you proposing a different set of variables here? My recurrence has only one argument right now. Okay? So then we need initialization conditions. Okay? So then now to actually solve this, we need to now come up with what the formula is, and then what the initialization conditions are. Right? What is your proposed formula?
Fn equals to fn minus 1 plus fn minus 2 plus fn minus 3 plus fn minus 1.
Fn minus 2 plus Fn minus 3, and you said plus another Fn minus 1. I am going to simplify that and to say this. Okay? So what you're saying here is that the number of ways of doing it are, you're going to peel off what the last digit is. In any string that does it, there is going to be a last digit. That's what you're arguing about, right?
Yeah.
And once you have the last digit, then basically, if the last digit is a 1 or a 4, we want to know how many strings are there, adding up to n minus 1 that we can prepend to this. Is that right? That's the reasoning here. Right? Now how many strings can we prepend up to 2 and prepend up to 3? Any questions about that? Okay. What are the initialization conditions? What are the boundary conditions?
F1, F2, F3.
Okay, we need to have, if we have a history of 3 in this recurrence, we need to have 3 initialization conditions. F sub, you say 1, f of 2, f of 3. Does that suffice? Do they ask, I don't know, does the problem give a possibility of f of 0? Is f of 0 ever an answer here?
No, n is larger than 1, 2.
Says that n is between 1 and that, so we don't need 1, 0. Although this would work equally well if we did have 0, right? Everybody agree with that? So what are your initialization conditions here?
1 is 2.
What?
1 is 2.
1 is going to be 2.
5.
2 is going to be
5.
5. And 3 is going to be
13.
what?
13.
13. Now, first question is, where did that come from? Okay, how did you get these initialization values?
1 is 1 and 4.
What?
1 is 1 and 4.
1 is 1 and 4, so 2 I'm capable of counting up to. I understand 2. How did you get 5?
It's 1 and 4. The first digit is 1, and I have two possibilities. The first digit is 4.
Okay, so you did this at the 13. How sure are you that it's 13 and not 14? You do this by brute force?
No, because the 13 is the first. I just tried the first digits. So.
Okay. The question that I'm wondering about, how many people did this problem? How many people did it in a similar way? Okay? Did everybody go through and count out the 13 possibilities for 3 by hand? Or was there a way that we could avoid having to do that?
It is stated the question.
What? Oh, actually, I see. So you're saying that the reason why you knew that was because that was being given here. Okay? If it hadn't been given here, you know how I might have done this?
I think I already have the recursive formula, so I can use that formula to compute it.
You could use, so one possibility is that the number of basis cases here may be a little bit complicated. There was no reason why you had to start your recurrence counting at 1.
I cannot start at 0 because the 3 has a different. Because I already have the digit of 3, so the F3 should be the computing of the F3 and plus 1.
Well, could we get it by knowing what f of 0 is?
No, I will get a 20. 12. I will get 12.
But why? How many ways are there to make 0 out of it? One. I would say there's probably one way to make 0 out of it. Does everybody agree with that? What's the one way to make 0 out of this? The empty string. Okay? If we have 0, 1 and 3, 0, 1, and 12, do we end up getting what we want? Okay? Now to get f of 3 should be equal to 2 times f of 2, right? Plus f of 1 plus f of 0. Okay? And here we would get 1, 2, 2 times 5, this would be 13. Does everybody see that? There's no real reason why you have to make the basis case. If your recurrence is right, you can often set your basis case back a little bit, and it becomes easier. That would be my one little contribution here. Okay? Any questions? Now, how did you evaluate this recurrence? Did you do it by dynamic programming, or did you do it by brute force? Recursive calls?
I just loop through it.
So you set up an array. I goes from 1 to 1,000, or whatever the upper limit is, right? And you filled in these values, knowing that at any point what you need are the 3 previous values. Is that basically right?
Yeah.
Okay. Anybody do it in a different way? Is there anybody who did this in a different way? In any way whatsoever? Subtle or not subtle? How many lines long was your program?
I think because I have a large number library, so about 120.
You said 120 because you had a large number library. Okay?
100 lines.
Did we need 100? Did we need a large number library for this? So let's think about it. Why did we? How clear is it that we needed it? Let's just stop to think about it. How many sums are there up to 1,000? What is the answer for up to 1,000?
At least 2 to the power of 1,000, because you can see the recursive volume is larger than 2f in minus 1.
That's a good answer. That is a good answer here. As far as figuring out what the rate of growth is, it's clear that it at least doubles every term. Okay? So that is a sign that you should need a large precision integer to deal with this. Okay? Any questions? Did anybody try this with how did people do the large precision integers? Okay? Did anybody do anything clever or not? What do you do?
High precision.
You say you use the library that you built, okay, for doing arithmetic. Actually, this is basically addition, right? I guess on one of the previous problems, we also did have addition of positive numbers, right? So I guess it didn't have to do anything more complicated than that, okay? Is that right?
It's more complicated because last time both strings are of the same name.
Okay. What was the last problem?
Reverse and add.
Reverse and add had the property, I guess it might have been a little simpler, but not except that much simpler. We do know an upper bound, we can still use arrays, we know an upper bound of 1,000 digits on this, right? So any other questions about this that makes it interesting or not? Okay? Any questions? How many people were sitting in here typing on their computer or on the web? Just out of curiosity. I'm not going to complain. I'm just curious. Because if so, one other thing about integer sequences I'd like you to do is to check out, well, I guess I am, right? One other thing that's kind of interesting, which I hadn't looked up yet, but let's see if we can look it up, that might be interesting about sequences like this. Is anybody familiar with the Handbook of Integer Sequences? Okay, let's type in Handbook, I assume it's still up, of integer sequences. Okay, let's say no. Let's see if this is around. Online handbook of, oh, wait, is that it? Move to there? That's surprising. Let me just take a look at this. Let's try this. Is this right? No. So there's a very interesting book. If you ever do stuff, have fun with integer sequences. This is an integer sequence. It's counting, as you notice, right? One interesting thing is that there is a very interesting reference book called the Handbook of Integer Sequences, which collects all interesting sequences of integers people have found in the literature. And so, for example, what are the first values of this sequence? Does anybody know? It starts at 1, right? 2, 3. Let's look at 1, comma, what was it? 2, 2, comma, 5, comma, 13. In search, we'll see there's a zillion integer sequences that start with that, right? Assuming this thing's live. What's the next number? Out of curiosity. Does anybody have their program running? Or we could evaluate the recurrence here. What's the next value? 35? What? Who said? You said it's 35? What is the next value here? Does anybody know? Okay, if not, we can evaluate the recurrence ourselves, right? 2 times this would be 26, right? Plus the previous 2 terms, which would be 7. 33. Does everybody agree with that? Let's see if this sequence is in the database. There is at least one other one that's in that database. Well, let's look. Well, here's 1. Okay, are there any other ones? What's the next number here? We still have 18 sequences like that. What's the next number? What? 84? 84? And 214? Let's see if we have this one here. Okay, still 2 of them. What's the next one?
The next one is automating something.
Wait, what is the next one? You mean it's 255?
The lower result is
Oh. Oh, okay. So in fact, is this the right sequence? That's interesting. What's the next one? Someone tell me what the next number is. Okay, what are the next terms in our sequence, just out of curiosity? What's the next number? No, I can read on here. The question is the one that you're generating the same one in the database?
Up to 12 in the bench.
The first 12 terms match. Okay? So likely this is the series that it actually appears in. Okay? And so what's interesting is we have now learned something about the sequence by typing this thing in. In fact, it's an expansion of this generating function. In fact, it's not at all surprising. This is, in fact, the right way to deal with it. This is a generating function. This would be a generating function of exactly this recurrence relation. If you look at it, it's got the 2x, x squared, x cubed. Okay? So what's interesting, just as a fun thing to do, whenever you have any kind of a numerical problem, okay, and, not necessarily for programming contests, but assuming you all go on to become mathematicians, whenever you have a numerical problem, this is actually a very interesting resource to find you once you have a start of a counting sequence, okay, to try to have you extend it, okay? Any questions about that? Does anybody else have any other favorite set of numbers, sequence of numbers they care about? We can look up while we're here. Okay? So if you're interested in integers and number theory, this is a fun thing to look at. Okay. Any questions? So I think we have dealt with this problem acceptably. Okay? Any other questions about the first problem? Okay. Let's look at the second problem, having to do expressions. Who's done the second problem? Okay, you've done the second problem. Anyone on that side of the room haven't done the second problem? Or tried the second problem? Okay. Someone tell me what the second problem is. Someone on this side of the room now. Okay, what's the second problem here? Yes?
Given the string length and the depth, find how many possible ways the string could be.
Okay, so we would want to write, we want to find correctly parenthesized expressions, and with the property that it uses no more than n parentheses, where n, I guess, counts both left and right parentheses, right? So n is always an even number. Is that right? And the depth of it, the nesting depth, has to be less than or equal. Is it less than or equal to d or exactly d? Exactly d. Okay? Any questions about that? So how do we do this? What is the basic strategy that we would use to count something like this? Any ideas? What would be the basic strategy that we could... One thing we could do, conceivably, might be to exhaustively construct all possible parenthesizations, filter them away and count them. That might be one way to do that. Is that a good or a bad idea? Bad idea. Why is that a bad idea? Because the claim is that the number might be very, very large. Does everybody agree with that? If I allow 300, where, how big can it be actually? That's a good question. Is this going to potentially overflow and require large integers? Maybe. Okay, I don't see any reason yet why not. Okay? And certainly anything that's going to count up the large integers would be a problem. So how do we go and do it? What is the basic strategy we need to do to solve this kind of accounting problem? You say cut it into two parts. I think what I would be saying, which we may be saying the same thing, is come up with a recurrence relation. Is that what you're saying? Okay. So let's come up with our recurrence relation for counting this kind of thing. Okay? First, what would we do? I would say it's got to be f of nd. Is equal to what? Right? The number of woofs. You know what a woof is? WFF. That stands for well-formed formula, meaning that it's properly parenthesized. With n parentheses and depth, you say exactly d? Does everybody agree with that? Okay? Now, how do we come up with a recursive-like idea to count these things? Okay? Any ideas from that side of the room? Was there anything we talked about last class about how we might count these things? Okay? What kind of numeric sequence does this smell like? Okay? Last class I talked about the Catalan numbers. Okay? Those of you who are here remember that, right? And the Catalan numbers counted the number of parenthesizations, but they didn't factor in the depth, right? So now we have to try to modify that kind of an idea, I think. That's basically what I think you're trying to tell me, right? How do we now do it? Can you propose to me a recurrence relation? Or at least an idea for a recurrence relation?
Sum up from I to n minus 1.
Okay, so we're going to sum up over all possible breakpoints k. Is that the idea? Something like this. We'll have to get our indexes right later on, right? So where did the Catalan number recurrence idea come from? It came from the idea that we found where the first pair ended. Okay? And what? And we then counted the number of solutions. If this was at position k, we knew how many parenthesizations there were there, right? And we didn't know about it, and then we have to count it here. Okay? So what is the form of what we're trying to look at here?
The depth of either side is d, and the other side is less than
Okay. So now the problem is going to be a depth of exactly D. Okay? So let's start to make a proposal on this. What's your initial version?
F K D
F of, if this is the kth spot, right, K,
D minus 1
D minus 1, because we're already in here. Okay?
and times
Times.
the sum of all F n minus K D.
Okay, so what you're trying to say here is, you're not going to say this is a sum of something. What are you summing it up as?
Sum let's say L
L as it equals from
from all number less than D.
0 to D minus 1, you want to say, right? Of what?
F n minus K minus 1.
Minus, you say 1. Let's say for now, what's the other one?
L.
L. Okay? How many people follow this idea? Let's think, any questions about what the idea here is? Okay, whether it's right or not, we'll have to decide. Okay? But the argument here is that he's going to say any parenthesization of depth D, what's in here is going to be 1 less, right? What's going to be in here is going to be unchanged. Okay? If the total, it's clear that any parenthesization with the following property, with the property that it has n pairs of n parentheses and a depth D, if you pull off the first one, the stuff in here gets lowered, its depth gets lowered, and the depth here gets unchanged. You're counting, and so what you're doing here is you're lowering the depth here within the first part. And you're saying that on the other part, it doesn't matter. It could be any depth up to D minus 1. Is that right? Okay. So what's wrong with this argument?
It assumes that the deepest will be the first parenthesis.
It assumes that the deepest one is going to be the first part. Does everybody see that? So somehow our parenthesization was ka-chunk, 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 ka-chunk. This would not be captured by your occurrence. Does everybody agree with that? So how do we modify that?
Plus.
What?
Plus.
You're gonna. Any questions? Okay. Well, we'll try it this way. Maybe there'll be other ways to do it. How are you gonna do it?
First I changed the L from there to D minus 1 to L from there to D.
Okay. L from there to D. To D. Okay. And now what are you going to change?
Because it came from 1 to N.
Now you're going to have a sum. Wait, first of all, is this now going to be completely, or are you bracketing this?
Yeah.
Okay. And what's the other one that you're counting?
Because they go from 1 to N.
Sigma sub k goes from 1 to n of what?
L from 0 to D minus 1. F K L multiplied by F n minus K.
Okay, you're going to give me a what's F n minus k what?
D.
D. Okay. So let's decide it. Okay, is this what we want here? Okay. I don't think that's quite right either. But so let's just think what our strategy here is, and let's see whether we're getting it right towards it. Okay. The first part is you're going to be telling me you're now going to do a case analysis to break it up into two groups, right? So what I would probably say is, conceptually, you're going to be making this as the sum of what we would call the woofs with first part, depth D. Is that right? Okay. And then plus the woofs plus with second part.
The first part is not that deep.
Right. Okay. Now you got to be careful not to double count. That's an important part here, right? If we just have it be the woofs with the first part, depth D, and the woofs with the second part, depth D, okay, this would double count, but not first part, D, okay? This would then be properly counted. Does everybody agree with that? So let's figure out now if the first part counts what you want it to count. And then if the second part counts what you want it to count. Is that right? Does the first part count what you want? The first part is, darn it, going to be of depth D. Because you're insisting that you're only allowing, you're saying k goes from 1 to n. F of k, d, yes, this is exactly of depth, the first part, right? And the second part,
I think that should be m minus k.
what?
I think that should be m minus k.
So you want to say this is n minus k. Okay, let's think about what it actually should be here. So you're telling me now you're going to count for all other depths at the other side. It could be depth 0. It could be up to depth D. Okay? This is counting all of them where the first part is of depth D. Agreed. Are there any other index issues though?
Well, n minus k minus 2 because the first bracket is just.
Does everybody agree that it's n minus k minus 2? Because he's peeled off the first two parentheses. Okay?
And the first x.
He's got k date parentheses. He's got, actually, is this k?
I think that it should be k from 1 to n minus 2.
Okay? 1 to n minus 2. Okay? Does this make sense? We have already accounted for two parentheses here. We can't use more than a total of n. So n minus 2, certainly that seems reasonable. Okay? And what about this part? The second part has to use n minus k minus 2 parentheses because we've accounted for all the rest of them. And the depth can vary from 0, meaning it's an empty string, okay, to a depth of up to d, okay? So this I now think I believe. Does everybody believe the first formula?
K can only be even.
Well, now k, according to this, the question is what do we do about k even or odd? Certainly in this case, k can be even or odd. We're going to have to deal with the fact that there can't be odd length formula.
I think we just define one case, or one case or the fk and d will be there.
So the two ways we could do it is, one is redefine what n is, define n to be pairs of parentheses, and reformulate it. The alternative would be to explicitly say that for when n is odd, set it up as a boundary condition. F of 2k plus 1 d is equal to 0 for all k and d. That would be another way to resolve it, right? I think doing it actually to program it, it's probably easier to deal with it in pairs. So I'm sort of, my heart is with him. But I think I'd like to finish deriving it this way, since we started dealing with it. Okay? Does everybody sort of get that? So what about the second one? Okay, what's the second recurrence? Does this count what we want?
No, k is from 1 to n minus 2.
K is going to go from 1 to n minus 2.
L is from 0
Okay, well, actually, wait, let's just think. Actually, is K equal to 1? Actually, does K go from 0? Why can't K be 0 here, actually?
Yeah.
Because we could have an empty string, in this case, K would be equal to 0, right? So I think K is equal to 0. Now the first part of it is of depth less than D, strictly less than D.
Yeah.
So I don't see any reason why, actually,
0 to d minus 2.
actually this should be 0 to D minus 2, because one level of depth is provided by the outside. Does everybody see that? I think I believe that. And this is saying that, darn it, because the second side has to have, this is going to say the first part does not have depth D. This one does have depth D. But what else do we need to change here?
Minus
Well, I think the minus 2 still needs to be done. Does everybody believe that? I think this recurrence is now right. Okay? Any questions? How many people believe the recurrence? How many people don't believe the recurrence? Actually, it's a good question. How do you test something like this? That's a good question now. Is there a way to test this? Rather than just, and one possibility is you implement it and you pump it off. Right? Any ideas how you might test this? You make some test cases. Now the trouble with testing something like this is these test cases are very easy cases, right? What you really would like is some harder case, okay, and have that materialize. How might you test this program before submitting it? Any ideas? Or would everybody just sort of type it in, let it fly, and see what happens? For our purposes here, you could probably do that. It doesn't cost you to submit. If you really wanted to test it, though, a little bit, if you were at a timed competition, what might be a special case of this you know what the answer is? Okay? I guess for the the Catalan numbers would work for the case of the sum of all depths, right? So one possible test might be, if you really wanted a test case, would be to compute this for all possible depths and see if that adds up to a Catalan number, which you do in principle know the right answer for, right? Again, I don't know if that means whether you let it fly or not. Is there anything we're still missing on this problem?
I think we can solve it better.
Okay?
We change f and d to the f is not exactly even, smaller or equal to d.
Okay. So now let's try a different formulation. What you want to say is, let's write it in a different color here. That's right. That's a pedagogically sound thing. You want to call now f sub nd is equal to the number of woofs with n parents and depth less than or equal to d. Is that right?
Yes.
Now, if this was easier to count, that's not quite what they're asking for. Does everybody agree with that? But does it give us the same information if we can compute it?
Yeah.
How would we do it? How would we get the one we want if we can compute this?
f and d minus f and d minus 1.
Right, so if we make this f prime, basically what this would say is that f of nd is going to be equal to f prime of n comma d minus f prime of what? N minus 2d. Because we're subtracting off two parentheses. Right? Because every no.
d minus 1.
f and
D minus
Oh, wait, no. What am I saying? You're 100% right. Okay, f prime sub n minus d, n comma d minus 1. Absolutely. Okay? Because this is summing the total up, all ways with depth up to D. This is the total ways of all the depth up to D minus 1. The difference from them are the ones with depth exactly D. Okay? So that I believe. Is that now easier to count? Let's come up with a recurrence for that one. Do we feel brave enough to erase this? Okay? Let's, it's funny. Before I erase it, let's go to the other side of the board. Or other side of the board. So camera track me. Okay. What is this now going to be? Okay. What is the formula for f prime n comma d? Okay. Anybody want to help develop it? Now f prime of n comma d. Let's just remind ourselves. Means depth less than or equal to d, right? That's the difference. So what is this formula going to look like?
Sigma k from 0 to minus 2.
Sigma, as k goes from
0 to n
0 to n minus 2, f k
d minus 1
comma d minus 1
multiplied by f n minus k n minus 2 d.
f sub k, no, f sub
n minus k
n minus k
minus 2.
minus 2 d. Is that what you're proposing?
Yes.
Let's think, is that right? Or are we possibly double counting? Okay, this is the danger this is the bane of these kind of counting arguments. Okay? So this certainly looks much simpler than the other one. Is this right, or are we double counting? Okay? This is saying that any expression, actually maybe we're not double counting here. Let's go back and take a look at it carefully. We are saying that anything that has a depth of at most d on these things has a first part of depth at most d minus 1 after we peel it off. And the other part has the part of at most depth d. Okay? We are not double counting. I don't see any evidence we're double counting here. Does everybody agree with that? So this is a much slicker recurrence than the other one is. Does everybody agree with that? That's a good trick. Okay? What are we missing still? There's still one thing we're missing here. What is it? Basis cases. What are the basis cases here? Okay? What are the base cases that we need to have? Okay, so one brave case here is you're going to tell me that f of 1, 1, f of 1, 1, well, first of all, 1, 1, we have to deal with the, there's this now the screwy thing still, with the, what do you call it? With the fact that we're dealing with double parentheses, that there's two parentheses, it's only defined for even numbers, right?
We can just divide n by 2. Divide n by 2.
Okay? So how do we want to deal with this one? Okay, one possibility is we really define now that to deal with this, we might want to define another function. I would say g of n d, which is equal to where n is the number of pairs. Right? Then say that f prime sub n d is equal to g of n over 2d. Okay? And then modify this to be g. How do we modify this to make it work for even numbers instead of for only the pairs of parentheses?
N over 2 minus 1.
Well, we did that n over 2 here. Now we call this as g. We have to make what changes?
N over 2 minus 1.
N over 2, this becomes a 1.
N over 2.
And this becomes a 1. Does everybody see that? and now we're living in only the world of pairs of parentheses. Okay? Do we want to work out the basis cases for the pairs of parentheses case or the real parentheses case? Pairs, okay? So what are the basis cases for this one? Okay? You could try to work it out for 1, but look at what the recurrence is doing. The D is going down to 0 at some point. Well, this could be large. This number is going to be going down to 0. Okay? So everybody, sometimes you're going to be changing. D might be relatively large. Sometimes this might be relatively large. Okay? I think the basis cases have to handle both extremes. Okay? What are the basis cases that are good for handling extremes?
I think G00 is equal to 1.
Excuse me, what?
G00.
G00 is equal to 1. You're telling me that, actually maybe I'll go right this back in. You're telling me that if we have 0 pairs of parentheses and 0 depth, there is one way to do it. Okay? That's plausible. Okay? I think I believe that. Although I always get fishy about these empty cases. Okay? But I think I believe you're right. What other basis cases are there? Is that all that we need?
G and N equal to 1.
G and N is equal to 1. Does everybody agree with that? That's a much more powerful example of this one. That there's only one way to deal with it. When you have a perfectly nested thing of depth n. Right? So this basis case I like. Okay?
No.
What?
The depth is at most n.
Ooh, but now we've got a depth of most n. So this is now a little bit trickier. Okay? So that's not so good anymore. Okay? So let's resurrect this one. What other basis cases are there? Okay? So I agree with you. Now that we're dealing with the someone, this basis case that I had in mind would work on the other side of the board. If this is going to work, we need the right basis cases. What are the right basis cases? Okay? Any other ideas?
N equal to 0 and D equal to any number.
Okay? So you're going to tell me G of n equals 0 to any depth. You say that's going to be equal to 1? This is why it's a little bit queasy. I would think it's 0. Okay? Because there isn't really any way to do it. Well, actually, wait.
Because it's
No, it's got to be 1. You're right. Because again, this is at most this. Because it includes that special case. Right? So I think I believe that now. I'll even get rid of my question mark. Okay?
actually for G and D. If D is larger than N, then it equals to G and N.
Okay, so what are you saying here? If it's G, what are you now proposing?
Equals to G and when D is larger than N.
So you're telling me that if the number of... okay, this is certainly true, okay, although this is a... that if you have greater depth than parentheses, you can never have greater depth than parentheses. That's certainly true, although I'd like to think that depending upon how you evaluate it, you would never get to that case. Okay? So this is true, but it's not clear to me that it's that helpful. Okay? Is there any other... does this...
But I think when you get an input, then when D is larger than N, it's useful.
Okay, so let's say we agree. Let's say we agree. Okay, that for larger. Okay, let's say I guess they didn't rule out that n is larger than d, right? So let's say we agree that that can be helpful. Okay, but for the basis case, but that's more for dumb input rather than the basis case. Do we have all the basis case that we need? I don't think we do. Okay. because this is going to, what's going to happen here?
N minus 1. N minus 1.
Okay?
We have N minus 1.
You have n minus 1 d. So what is it when we have actually n comma 1? Maybe this is a special case that is interesting. When there's a depth of length 1, okay, for any n, do we know what that answer is? 1, right? Because if there's depth of length 1, it's got to go ka-chunk, ka-chunk, ka-chunk. And this may be enough to finish the job. Okay? Let's think about it. Here's one where this is big and this is small. This is one where this is small and this is big. Okay? And these might be enough to finish the job now. Does everybody sort of agree? Do we need anything else? Because if we keep dealing with this thing, eventually, n and d, eventually this is going to have smaller values of n, okay? And eventually, n would be 0, okay? Let's say these should be enough to do it, okay? Any questions? Now, for these to be enough to do it, we now need one more thing. What is the other thing we need to do to implement this thing? Do we need anything else to write this program?
Large number.
You say large numbers, you had large numbers from your previous thing, so you already have that one. Anything else that we need? We need an evaluation order, it seems to me. So if you want to do this, again, it depends how you're going to be doing this. Are you going to be doing this by memoization and recursion? Or are you going to be doing this by finding an order and having for loops? Who did this by for loops? Who did this by memoization? Okay? I like thinking about for loops. What is the right, let's say, evaluation order here? Okay? Someone want to propose my loops?
Fix n and loop d.
Fix n and loop d. For n equals 1 to n. Okay? For d equals 1 to 0 to d. Okay, is this what you're proposing?
No, d is from 0 to n.
D is from 0 to, well, n, okay? But you're filling out the whole table now, right? Okay? Actually, and you want to say now you're going to evaluate. Okay? G sub n comma d. Okay? And we believe that we will have, at first,
I think if you do not memorize, d will be sufficient.
what?
If you do not memorize all of them, then d is from 0 to d is sufficient.
0 to d, the input depth is what you mean.
Yeah, because this recursive formula d is always smaller than.
Right, okay? So this is how we didn't really need this case that much, except for your test case. Okay? And if we do this, do we know the values? Okay? We're going to have, first of all, for 2, the first interesting case is going to be n equals 2. D equals, okay, we're going to know for 2, 1 we know. Then it's going to be 2, 2. And that's going to depend upon the smaller values. So this is an acceptable evaluation strategy. Any questions about that? Okay? I think this works it out. And the lessons here are that there is sometimes a simpler recurrence. Okay? And it pays to hunt for it. Okay? How many lines long are your programs? Who got it working? How many lines long was your program? Let's start with you guys in the front. How many lines long? 100. How many lines long was yours? What?
He definitely cannot remember.
He definitely can't remember.
I guess mine is 150.
150. Okay, and how long was yours? Did you get yours working or no?
I'm just writing it.
Well, don't write it now. You're supposed to listen. Okay, don't write it now. Okay? Any questions? Okay, so why was yours 150? Any particular?
Library.
Because my library is 150.
I see. So most of this stuff is the math again. Okay, the long persistent integer arithmetic. Any questions? Okay, but I think that's an instructive one. Okay, any other questions about this assignment, this problem? Okay, what about the next one? The Towers of Hanoi problem. Okay, let me get this thing here. Who's tried this one? Okay, on that side, tell me about this problem. You. Okay, so let's just go through this again. The Tower of Hanoi, where we have, instead of our 3 pegs that we're used to, okay, we have more pegs. Does everybody agree that as you add more pegs to the Tower of Hanoi problem, it becomes easier and easier? Okay? Easier in the sense of requiring less steps. Remember, the story of this was supposedly that the world comes to an end. There's these priests in this, in I guess, Hanoi. Okay? Busy trying to do this, and when they finally move all the pegs, the disks, the world comes to an end. That's the legend here. Okay? Now, if they had set up a lot of pegs, they could end the world very quickly. Does everybody agree that if I had n, how many moves would it take if I had n disks and n pegs? What? N. Does everybody agree with that? You simply put it down, well actually 2n I think, right? Because I have to move every one to its own peg. Okay, I think I have 80n plus 1 pegs, right? I need to put the biggest one on its own peg. And then I put everybody else back. So the problem only becomes hard because I don't have enough pegs to put things down, right? Okay? So now the question is about 4 pegs. And what they do is they give you a proposed strategy here. Is that right? That's what you were telling me, right? What is the proposed strategy? Top K disks someplace else, right? Okay. Top K disks using all 4 pegs, right? To here.
And then we just follow the previous method
Then we would move the top, the remaining pegs from here, disks from here, to where we want them. But we only have 3 pegs now, right? Because one of our pegs is clotted up. Because we can't put the bigger disk on top of the ones that we already moved. Does everybody see that? And then what you're saying is, now then, you've got to remove these remaining K disks over to here, but you can use all 4 of the pegs as you want. Okay? Any questions? So what is the, and your goal is to figure out how many steps it takes, is that right? So how do you do it?
I build the rules that, for example, if there is 10 days, I have to check, because this question we have to check the value of K. So I have to check from 0 to 9 to check on which K is.
Okay. So you're telling me that the problem is that they didn't tell you what K was, right? And you have to find that. So to find that, if it's a counting problem, is there a way to write this as a recurrence relation? That's how I would try to do it, right? Is that what you were doing? So let's write the recurrence relation. What are the arguments to our recurrence relation? F sub. What?
There is a model
You're going to go with a what? A formula?
for loop.
A for loop. Okay? Let's see if there's a recurrence relation for this, because I like recurrence relations. I think recurrence relations are really good things. Okay? Is there a way to write this as a recurrence relation? What would be the way we would write it? Okay? Okay? What are the arguments to our recurrence relation? F of n. Is there another argument that's interesting? I want to say, I'm going to put an extra argument in here, just because I feel like it. Fn p for the number of pegs. Okay? And this is going to be equal to the number of moves for n disks using p pegs. Okay? This is the way I would write my recurrence. Okay? If so, what is the recurrence?
Max. Minimum.
You want to say the min over k as it goes from 1 to n minus 1 of what? F, K, comma, P, plus
N minus K, P minus 1.
F, K,
N minus K,
N minus K,
P minus 1.
K, N minus K, P minus 1,
Plus
plus what?
the first.
Is this what you're trying to say? Because here what we're saying is, we're going to decide to stop at some value of k. We don't know what it is, right? Okay? But the k that minimizes this. Okay? Any questions? Actually, what's neat is now they give you 5 pegs. This is in principle also possible, right? It gives you a reasonable thing if they give you 5 pegs. You now have a reasonable strategy. It's a little more general than just for the case of 4 pegs. But what are the boundary conditions here? F sub n comma 3 is
2 raised to n minus 1.
okay. What he's saying is for for 3 pegs, he knows the answer because he studied the Tower of Hanoi in previous lives, right? What is the number of steps for a to do it? He's telling me that it's 2 to the n minus 1. Is that right? Do people believe that? Who here believes that? Who here doesn't believe it? Okay? I don't know if I remember such things exactly, but I might try to solve a small problem to convince myself. But everybody's convinced of that. Is there anybody who's not convinced of it? Okay? Let's say that that's true. Okay? Is that the only other case that we need to worry about? Okay? Or do we have any other boundary conditions? Okay? Any other boundary condition here of interest? Okay? I'd like to think that there is, because somehow this value is not going down, right? So you need to have some kind of a boundary case for the case of 4 pegs. What boundary cases for 4 pegs do we have? F of what?
0. Or 1 piece. 0 piece 0.
0?
I think 1 is
0 sub p is going to be equal to 0. That's certainly true. But I don't know if that's a powerful enough thing. Okay? It might be, but I'm not sure it is. Is there any more powerful basis case that we know? Yeah?
Maybe for n
Okay, so what you're trying to tell me is f of n comma p is equal to 2n for n less than, is it less than p or less than or equal to p? I think it's less, well, let's think about it.
Okay, now equal. Less than.
I think it's less than, right? Because if I've got 3 disks here, okay, I've got trouble, right? I guess if it's 3 disks, I'm okay, right? 1, 2, actually,
I think it's 2.
this isn't quite the right one. It would be 2n minus 1, I think. Let's get this right, okay? How do I do it? I start out with the case of n equals 1. For n equals 1, it's going to be 1. Does everybody agree with that?
But if n equal to 1, you don't need to move it.
You need to.
Oh, that's a good question. Do we have to move it in the case of 1?
Yes. We need to move it from the first to the last.
I think you have to move it from the first to the last, right? So that's the way that, that maybe that if it's 1, you can just walk away. But if that was true, you could have walked away from the original Tower of Hanoi problem, right? You could just say, well, I'll just turn the whole set around, or I'll walk to the back, and now it's done, right? So that's not right. So you do have to move it. So I think the answer is it'll take 1 step. Here is n, and here's the number of moves for 1. It would take 1 step. For 2 disks, how much time would it take? 3. For 3 disks, how much? 5 up until it. So what's the right formula here? Is it this? 2n minus 1? For n equal to 1, this is going to be 1. For n equals 2, that's fine. And where is the value of n where we get into trouble?
1 and 2.
What?
1 and 2.
No, it has to do with when n is bigger than, I guess when n is equal to the number of pegs. That's not okay. Right, so long as n is less than the number of pegs. I think this is the right boundary condition. Any questions about that? Okay. And again, this becomes relatively easy once you know how to deal with recurrence relations. Does everybody see that? Any other magic on this problem? Yes.
I have another approach to solve this problem, but I don't know how to prove it.
Okay. What's your approach? Come here.
When I use this to solve the problem, I find that this 1, 2, 3, 4, 5, 6, 7, 8, okay, 5, 9, 13, 17, 25, 33, and
What are those numbers you just wrote down?
let it be Fn, okay?
Okay.
F n minus F n minus 1 equals plus 1 plus 2 plus 2 plus 3 plus 4, yeah, plus 4 plus 4 plus 4 plus 8. Here is only 1 plus 1 and 2 plus 2, 3 plus 4, 5 plus 8. But I don't know how to prove it. But I try to write a program and submit the answer and it give the right answer. But I don't know how to prove it.
So what you're saying is an interesting question. Okay? You're saying that it goes by the form that it's going to be count by 2 ones here, then 2's here, then 3's there. Everybody see that? Now that could, you're saying that you think what you're doing is not only have you given the recurrence, but you're saying you think you have solved the recurrence. Okay? That you have some kind of a hard to describe, but in principle, or maybe hard to write algebraically, but easy to describe closed form for it. And the question is, how do you prove that this is the solution to that? Okay? Any ideas how you might prove that? Okay? First I'll say it looks a little complicated. But I would say the technique that I would use to prove it, at least I would try to do it, is what? I'm not going to come up with a proof now, but what would be the technique that you would use to try to prove this? Induction. Induction is the magic way to prove solutions to recurrences, right? And so one possibility is to say that you can maybe prove it by induction on, K. Okay? Where K is some argument there. That's one possibility. What is some other way you could satisfy your curiosity about this? If you don't want to do the inductive proof. Okay? What possibility is you go to the Handbook of Integer Sequences and you type in what these numbers are. Okay? And what will that tell you? Okay? That will probably tell you, I guess, okay, that somebody else has stumbled across this sequence of integers before. And if so, they will probably point you to a paper on it. Does anybody know these numbers well enough? You want to try it? This is kind of interesting to me. I always like doing this. What are the numbers here? Somebody want to... Where is it now? We had it here, right? What are the numbers here? Does anybody want to give me what the numbers are for this? Tell me now. 1. What's the next one? What? 3. Next one. 5. Next one. 9. Next one. 13. Next one. 17. Next one. 25. 33. 41. 49. Let's try this one now. See if we have enough terms. Okay, we have one sequence now. Okay, and son of a gun, what does this tell us here? This is the frame Stewart. Okay, the number of moves needed to solve the Tower of Hanoi problem with 4 frames and disks. Okay? And what does that now tell us? More to the point, if you're really mathematician-like things, this is really great. It actually gives you the point of papers on this. So if you want to check out your conjecture, undoubtedly, if it's a reasonable thing to be proven, one of these sources probably has it, right? And so a way to do more research on the problem, to save you from doing the inductive proof, is to go there. Okay? Any questions about it? Okay? I think that's pretty cool. Okay? So you'll learn something about how to do integer sequence manipulation. Again, during contests, you're not allowed to use this, okay, mercifully. But it's a very useful resource. Any questions? Okay. The last problem I'd like to talk about is a self-describing sequence. And I guess we've still got a little bit of time. Any questions? How many people got this problem? How many people didn't get it? Who tried it? Okay, somebody who got it, tell me what the problem is quickly. Okay? Somebody who got it, tell me what the problem is.
It's about function.
Function. Okay, what's the function? The function is, again, that we want to figure out what is the position. We want to know what is the value of f of n, where f of n is described by that there's 1, 1, 2 2s, and then that f of n is now going to be described by this. So somehow f of 3 is going to be the third value. We have 1, 1, 2 2s. F of 3 is going to be what the third value of it is. That's how many 3s there are. 2 3s. F of 4 is going to be how many 4s? There are 3 4s. F of 5 is how many 5s? F of 6. Okay? Your goal is to calculate what f of n is. Any questions? Okay? How would you do this problem? What's the simplest way to do this problem? Okay, at least the naive way to do this problem.
I'm marking the first occurrence of n in fn. I just do a reverse function.
Say a reverse function. What do you mean by that?
I mean the I define that f prime n is f prime 1 is 1. f prime 2 is 2, f prime 3 is 4, f prime 4 is 6. Just the first occurrence of this network.
Okay, so what you're going to want to figure out is where, okay, so one possibility is we construct this array explicitly. And the problem with that is what? This is an easy function to compute in an array. But what's the problem? Too large. Why is it too large? What are they asking you about? They said n can be up to 2 billion, is that right? Or 2 million? Billion, that's a big number, isn't it? Okay, so we can't have 2 billion members in my array, right? Instead, what you're going to suggest is, show me where is the first position, a more concise representation, you're saying, is the first position of where there's a 1, 2, so it would be 1, 2, 4, 6, 9, right? Where the first position of each one of these numbers. Is that smaller than the other representation? Yes. How much smaller? Okay.
I think it's about log relation.
You think it's a log relation? I don't really think it's a log relation. What do you think it is? I think it's more like a square root, right? Because it's sort of like the sum as I goes from 1 to n. So my belief is this is something, and again, we're going through it kind of quickly now because I do have something else I wanted to do. I want everybody to, it's something going to be something like the square root of n. Okay? Exactly what it is worth thinking about. And if you do it that way, that would encode it in smaller space, and then you have to look it up properly, right? Okay, and that's probably a reasonable thing. Any questions? Okay? Fair enough. What I would like to do now, again, I think people can think about it. That's maybe a slightly less deep problem, so I think people can figure that one out. I'm passing out now the assignment, which maybe I'll review more next class, but I just want to quickly go through it. This is going to tell you what I wanted. I promised you that you had one other assignment outside of programming, which was the 100 problem read. What I would like you to do then is to read a block of 100 programming problems. And for each problem, I want you to give me a one-line output for it. Okay? And I give examples on the back for 3 problems of my one-line output. For the purposes of today's discussion, we'll talk more about this next class because we're running out of time. What I'd like to make sure is that everybody finds their own block. Okay? So I'm giving each person in here a class set of 100 problems that's different than any other student in the class. Okay? I want you to go on the back. There is I see 2 matrices. There is a volume number and a 5-digit number. That 5-digit number is supposed to be the first 5 digits of your university ID. Okay? Which I was told last time was somehow cryptographically secure. It's not such a big deal. Okay? I want everybody to find their ID. Does everybody see that their first 5 digits of their university ID is up there? Okay? Who has found if you found your ID, raise your hand. If you have not found your ID, raise your hand. Keep looking. Okay? Now have you found it? Okay? Have any of you found the same ID? Hopefully not. Okay? I don't believe that's true. Okay. Is there anybody in here who has any objections to me posting this document on the web? Meaning that the existence of these 5-digit numbers. Does anybody believe that this is confidential information and that you wouldn't want somebody else to see it?
I have a problem. The last volume has not enough problem.
Okay, so does that mean you got the last problem?
No.
Okay. Okay. So I believe that that there is one person who may have something like 86 problems instead of 100. If you find that you are that person, come and talk to me. Okay? because I'm hoping that if it will go up to that it will go up to 100 by the end. Okay? Any questions here? I believe it's pretty full now, but if there's somebody who realizes they're getting off easy, let me know who you are. Okay? I won't necessarily punish you, but I would like to know who that is. Any questions? Read through this. We'll talk more about this assignment next class, along with the next batch of problems. Any questions? I think what's the next topic? I think the next topic is number theory, if I'm correct. Am I right here? Yes, number theory, which is a very interesting area, and another place to play with Sloan's Handbook. Okay, thanks for your attention. See you guys next class.